All right, welcome everyone to this explainer on media access control, or MAC for short. If you're an undergraduate taking communication engineering right now, you already know that MAC is absolutely the backbone of multipoint and broadcast links. Without it, networks would just be a total mess. So today we're going to bridge those intuitive physical concepts you've been learning with the actual rigorous mathematical proofs behind them. We're looking at exactly how multiple devices manage to share a single communication medium without their signals just colliding into total chaos. Let's dive in.
So here is our roadmap for today. We'll start with an introduction to channelization, then look at FDMA for dividing by frequency and TDMA for dividing by time. After that, we're going to get into the mathematical magic of CDMA, actually solve a CDMA code together, and finally wrap up by comparing these MAC protocols. Okay, let's jump right into section 1, Introduction to Channelization. At its core, channelization, which you might also hear called channel partition, is really just about fair sharing. Imagine a single pipeline of data. If every station on the network tries to shove their data through that pipe at the exact same moment, you get collisions. Nobody wins. Channelization solves this by partitioning the available bandwidth of a link among the different stations. And as we'll see, we can actually achieve this sharing across 3 completely distinct dimensions: frequency, time, and mathematical code. Moving on to our first method, section 2, FDMA, or dividing by frequency. To use a simple real-world analogy here, think of this approach like putting pairs of communicating people into completely separate soundproof rooms. In frequency division multiple access, the available bandwidth of the common channel is sliced up horizontally into dedicated frequency bands. Station 1 gets the top band, Station 2 gets the next one down, and so on. Crucially, each band is reserved for its specific station 100% of the time. They literally never talk over each other because they're confined by bandpass filters. And to be extra safe, we use small guard bands, think of those as the thick walls between our soundproof rooms, to ensure there's zero overlap or interference. Real quick, before we move on, I want to clarify a classic exam trap that catches a lot of engineering students. Do not confuse FDMA with FDM. FDM, or frequency division multiplexing, is a data link layer method. It uses a single physical multiplexer device to combine low bandwidth channels into one big high bandwidth channel. FDMA, on the other hand, is a physical layer technique. There's no central multiplexing device at all. Instead, each station independently generates its own bandpass signal. Definitely keep that distinction highlighted in your notes. All right, let's look at the next dimension, section 3, TDMA, dividing by time. So if FDMA is putting people into separate rooms, TDMA is putting everyone into one massive room, but using a strict timer so they have to take turns talking. Here, stations aren't restricted to some narrow little frequency band. They actually get access to the full bandwidth of the channel, but strictly only during their assigned time window. Station 1 transmits its block of data, then pauses. Then Station 2 sends its data, and so on. It's basically time sharing on a macro scale.
Now, while TDMA sounds pretty simple in theory, it presents a massive real-world engineering hurdle, and that is synchronization. Think about propagation delay like yelling across a massive canyon versus whispering to someone standing right next to you. A signal from a distant station naturally takes a lot longer to arrive than one from a close station. So to fix this, engineers use preamble bits at the very start of each slot to help the receiver sync up. They also have to insert guard times, which are buffer periods between the slots to prevent overlapping if a signal happens to be slightly delayed. And finally, it requires incredibly strict logic. The data link layer has to precisely instruct the physical layer exactly when to open and close that transmission window. Okay, now for the really cool stuff. Section 4, CDMA, the mathematical magic. We've thoroughly covered the physical domains of frequency and time, right? Now let's plunge into the abstract mathematical dimension. To really grasp CDMA, imagine a large room filled with a bunch of people talking at the exact same time. It sounds like absolute chaos. But what if 2 people are speaking English and they are literally the only ones in the room who understand it? They can hear each other perfectly. Filtering out the rest of the chaotic room is just background noise. Another pair could be speaking Chinese, sharing that specific code. In code division multiple access, the room is the common channel, and the different languages are unique mathematical sequences. Everyone transmits at the exact same time on the exact same frequency. This perfectly illustrates the math behind that language analogy. Every station multiplies its specific data by its unique code sequence.
The channel simply acts as an algebraic adder. It just carries the combined sum of all these transmitted signals simultaneously. It looks like a complete mess, but look closely at the recovery math. To pull out just station 1's data, the receiver multiplies that entire combined channel mess by station 1's specific code. And thanks to the magic of these mathematical codes, all the other signals simply cancel out, leaving only station 1's data.
Which brings us to section 5, actually solving the CDMA code.
So how does a receiver actually extract just one conversation from that chaotic combined signal? Well, let's walk through a complete problem-solving exercise together. Before we can do the linear algebra, we have to translate binary computer data into a mathematically workable format. Engineers follow 3 strict encoding rules here. A data bit of 0 translates to a mathematical -1, a data bit of 1 translates to a +1, and if a station is silent or idle, it translates to 0. This shift from binary bits to polar values is exactly what allows the signals to constructively and destructively interfere on the channel. And 0 is the absolute mathematical magic number here. The codes assigned to stations are called chip sequences, and they are perfectly orthogonal. What does orthogonal mean in this context? Well, it means if you take the inner product of 2 different sequences, multiplying their elements and adding them up, the result is always 0. For example, if you take the sequence +1, +1, -1, -1, and multiply it by sequence +1, +1, +1, +1, you get 1 + 1 -1 -1, which equals 0. This is how interference is completely mathematically erased. It is incredibly elegant.
Let's look at a concrete numeric example to lock this in. Say station 1 sends bit 0, which we know encodes to -1. Station 2 also sends bit 0, so that's -1. Station 3 is silent, so that translates to 0, and station 4 sends bit 1, which encodes to +1. Each station multiplies its data by its unique 4-chip sequence. When you algebraically sum all 4 of those resulting vectors together, the channel carries the composite sequence, -1, -1, -3, +1. Just take a moment to appreciate this. That single sequence contains all the concurrent data from all 4 stations mashed together.
Now for the really fun part, the recovery. Let's say our receiver only wants to listen to station 2. The receiver takes that composite signal we just calculated, -1, -1, -3, +1, and multiplies it by station 2's specific chip code, which happens to be +1, -1, +1, -1. Doing the inner product slowly here. -1 times 1 is -1. -1 times -1 is +1. -3 times 1 is -3. And 1 times -1 is -1. Summing those up graphically integrates the area, which gives us -4. Finally, we divide by n, which is the number of stations, so 4. -4 divided by 4 equals -1. And what does -1 map back to? Bit 0. We perfectly extracted station 2's data without a single drop of interference from the others. Boom. Now, to make this work at scale in the real world, you might be wondering where on earth we get these perfectly orthogonal codes. Engineers generate them using recursive matrices called Walsh Tables. You start with a simple 1-by-1 matrix of +1. To make a larger table, you duplicate the previous matrix into the top left, top right, and bottom left quadrants, and then you put the inverse of the matrix in the bottom right. The one strict rule here is that the number of sequences, n, must be a power of 2. So if an engineer is designing a network for, say, 90 stations, they can't just make a 90-station table. They have to jump up to the next power of 2, generating a Walsh table for 128 sequences. Let's bring it all together now. Section 6, Comparing MAC Protocols. Consider this synthesis table your ultimate study guide. It beautifully summarizes how each protocol solves interference. We have FDMA, which relies on physical frequency division, but it suffers from wasted bandwidth if a station happens to be idle. Then there's TDMA, which uses time slots for bursty transmission, but it faces immense synchronization challenges due to those variable propagation delays we talked about. And finally, CDMA, which allows concurrent full bandwidth transmission through the sheer magic of mathematical codes, trading the physical simplicity of the other two for highly complex signal recovery and processing overhead. As you review these concepts and practice the math for your engineering exams, I want to leave you with a final challenge to ponder. Based on the physical limitations of frequency and time versus the processing overhead of mathematical codes, which of these protocols, or perhaps even a hybrid combination of them, do you think scales best for the billions of massive concurrent connections required by modern Internet of Things networks? It's a real-world problem engineers are tackling right now. Keep digging into the math, and I'll catch you in the next explainer.